In this lecture, we continue our discussion on the maximum flow problem. In the previous lecture, we introduced the maximum flow problem using this example. We also tried to evaluate the maximum flow possible by considering the paths in a certain order, and when we did it with this particular order, we got a flow of 50 units. We first consider 1 to 2, 2 to 4, 4 to 5, 5 to 7, 1 to 2, 2 to 4, 4 to 5, 5 to 7 with flow equal to 10, and then we considered the other paths in this order and we obtained a flow of 50 units. We also worked out the same problem by considering the paths in a different order. Now with these 4 paths we were able to get 55 units. We also defined what is meant by a flow augmenting path. In fact, if we had considered the path 1 to 2, 2 to 4, 4 to 5, 5 to 7, which means we have a path from 1 to 2, 2 to 4, 4 to 5, 5 to 7. We realize that each of these arcs 1 to 2, 2 to 4, 4 to 5 and 5 to 7 have some spare capacity. 1 to 2 has a capacity of 40, 2 to 4 has 10, 4 to 5 has 20 and 5 to 7 has 30. Now out of these capacities, the minimum being 10, that is the maximum flow that can be augmented into the flow augmenting path. So this flow augmenting path 1 to 2, 2 to 4, 4 to 5, 5 to 7 gave us flow equal to 10. So we also defined a flow augmenting path this way as a path that connects the source to sink through a set of forward arcs 1 to 2, 2 to 4, 4 to 5, 5 to 7. When I say a forward arc, I mean when I say 1 to 2, there is an arc from 1 to 2, there is an arc from 2 to 4 and so on. Now if this path is made up of completely forward arcs and each forward arc has a residual capacity which is strictly positive, then the minimum of those capacities will now become the flow. Now such a path is a flow augmenting path. We also observe that all these were flow augmenting paths because they were able to augment the flow by a strictly positive quantity. In the second way in which we did it, we considered flow augmenting paths which gave us 55 units of flow. Now we also observe from these two instances that this can further be improved to get the additional 5. So let us again work out this 50 on the network and then show how we have to redefine the flow augmenting path so that we are able to increase the flow from 50 to 55. When we evaluated this 50 based on this definition of the flow augmenting path, we realize that there are no more flow augmenting paths. Therefore, we have to redefine the definition of the flow augmenting path so that we are able to increase the flow from this to this. So let us go back to this example to see how these flows are captured on the network. So 1, 2, 4, 5, 7 would be 1 to 2, 2 to 4, 4 to 5, 5 to 7, 40, 10, 20 and 30, minimum being 10, we have indicated this as flow equal to 10. Now this is updated as 40, 10, 10, 10, 20, 10 and 30, 10, where the second part gives the actual flow while the first part gives the capacity of the arc. We then consider the path 1, 2, 5, 7, 1 to 2, 2 to 5, 5 to 7. Now here there is a capacity of 30 because the total capacity is 40, there is already a flow of 10, so remaining or residual capacity is 30. 2 to 5 has 10, 5 to 7 has 20, so the minimum among this 30, 10 and 20 is 10. The flow is now augmented by 10, so we get this 10 becomes 20, this 10 is consumed and this 10 also becomes 20. We now consider the third path 1 to 3, 3 to 4, 4 to 5 and 5 to 7, 1 to 3, 3 to 4, 4 to 5, 5 to 7. Here there is capacity of 40, there is no flow, so all the 40 is available, all the 15 is available. Here 10 units are available, 20 minus 10 is 10, 30 minus 20 is 10. So, the flow can be augmented by a further 10 which is here. So, we update this 40, 10, 15, 10, 20, 20 and this becomes 30. Now, we consider the next path 1, 3, 4, 6, 7, 1, 3, 4, 6, 7. Here there is a capacity of 30, here there is capacity of 5, here there is 10 and here there is 20. So, 30, 5, 10 and 20, the smallest number is 5. So, the flow gets augmented by another 5. So, we update 1 to 3 is 15, 3 to 4 is also 15, 4 to 6 is 5 and 6 to 7 is 5. We then look at the path 1, 3, 6, 7, 1, 3, 6, 7. Here 25 is possible, 40 minus 15, 3, 4, sorry, this. So, 1, 3, 6, 7, 25 is possible, here 20 is possible. Right now, we do not have any flow on the arc 3, 6. So, 20 is possible, 6, 7, 15 is possible. So, 25, 20 and 15. So, we take the minimum of them which is 15 and therefore, this gets augmented to 30. This becomes 15 and this becomes 20. This becomes 20. Now, we have a total flow of 50. Let us also check whether we can have any more flow augmenting path. Now, for the path 1, 2, 5, 7, no more flow is possible because this is exhausted. 1, 2, 4, 5, 7, this is exhausted as well as this. 1, 2, 4, 7, this is exhausted. 1, 2, 4, 6, 7, this is exhausted. Now, with 1, 3, 1, 3, 4, 5, 7, this is exhausted. 1, 3, 4, 7, this is exhausted. 1, 3, 4, 6, 7, this is exhausted and 1, 3, 6, 7, this is exhausted. So, by this definition of flow augmenting path, we do not have any more flow augmenting path. Remember once again the definition of this flow augmenting path. Consider a path from I to j which is made up entirely of forward arcs and evaluate the excess flow that the arc, each of these arcs can handle, and the minimum of them is the flow that we can augment. Now, if we consider all these flows, now we are unable to get a flow augmenting path and therefore, we stop at 50. Now, how do we increase this 50 from 55? As I said, we have to now redefine the flow augmenting path idea, so that we are able to increase the flow further in this network. Now, how do we do that? Now, let us go back and consider a path like this. Now, with these kind of arrangements, with this capacity and with this flow, let us consider a path like this. Let us consider 1, 3, 6, 4, 7. Now, we are looking at 1 to 3, 3 to 6, 6 to 4 and 4 to 7. Now, 1 to 3 is a forward arc, there is an arc from 1 to 3. 3 to 6 is a forward arc, there is an arc from 3 to 6. 6 to 4 does not, there is no arc in this network with 6 to 4, but we are still considering it because there is an arc from 4 to 6, and then 4 to 7 is a forward arc with an arc going from 4 to 7. Now, if let us consider this once again. Now, 1, 3 I call it as a forward arc, because there is an arc from 1 to 3. 3, 6 I call it as a forward arc, 6 to 4 I call it as a backward arc, and 4 to 7 as a forward arc. Now 6 to 4 becomes a backward arc because there is a forward arc from 4 to 6. So wherever there is a forward arc from I to j, we may consider j to I as a backward arc under an important condition. Now in this, if we observe, if we look at 1 to 3, 1 to 3 is a forward arc with capacity 40, flow 30, so there is an excess 10 that it can absorb. Now the increase that is possible here is 40 minus 30, which is 10. 3 to 6 is again a forward arc, capacity is 20, flow is 15, so this can absorb 5, which is the difference between 20 and 15, which means the flow can be increased by 5 units here. Now if we look at this backward arc 6 to 4, there is a forward arc 4 to 6, and more importantly there is a flow in the direction 4 to 6. So this flow of 5 can actually be reduced or diverted, and therefore we consider the possibility of considering only this flow if it is a backward arc, so that this flow can be diverted and the total flow can be increased. Now we again go back to 4 7, 4 7 is a forward arc, there is capacity of 10, flow of 0, so there is a 10 that is possible. Now look at the minimum of these numbers. Minimum is 5. Now this 5 or this 5 is either the minimum of the capacity, the additional possible flows in the forward arc and the actual flows in the backward arc. So whenever we consider a backward arc into a flow augmenting path, we have to ensure two things. One is there is a forward arc in that direction. So when we considered 6 4, we know that there is an arc 4 6 in the network, and more importantly this has a strictly positive flow which can be diverted. So by considering this backward arc, this flow augmenting path which comprises of forward arcs and backward arcs, we can augment the flow by 5. So we can go back and add 1 3 6 4 7, which will give us 5, and we get that 55. Now the flows have to be updated. Now this 30, this is a forward arc, so 30 will become 35. 3 to 6 is a forward arc, 15 will become 20. 6 to 4 is a backward arc, so 10 will become 0. Now 4 to 7 is a forward arc, so it gets increased by 5. So wherever there is a forward arc, there is a flow, there is an increase. Wherever there is a backward arc, there is a decrease. So it is absolutely necessary that when backward arcs are considered, there should be positive flow, and by diverting that positive flow, we will be able to increase the total flow in the network. Now we can go back and show that this kind of a flow representation actually corresponds to this solution, and the maximum flow that we got is 55. So at the end what we have to do is, we have to now start defining the flow augmenting path in two ways. So flow augmenting path it is a path from source to sink made up of forward arcs and backward arcs. Such that for every forward arc in the path, the present xij, Cij minus xij, if let us call the capacity as Cij, or we may call the capacity as Uij, Uij minus xij is strictly greater than 0, and if it is a backward arc, then there is an xji in the forward direction, only then it becomes a backward arc, and the flow xji is strictly greater than 0. So when we do this, then we take the minimum value of the uij minus xij if it is a forward arc, and the flow xji if it is a backward arc, and then take the minimum of these, and all of these being strictly positive, the minimum will be a strictly positive quantity, and the flow gets increased by that quantity, and correspondingly if it is a forward arc then this increases, if it is a backward arc then this decreases. In this case we earlier had 5 and now it has decreased to 0. So, this essentially means we are actually taking away this flow and redistributing it here, so that this flow goes into this, and then there is an additional flow that can come into this network because of the redistribution that we have actually done. So, one has to understand that we are not deleting any flow, we are only redirecting or redistributing this flow whenever a backward arc comes into the flow augmenting path. So, the flow augmenting path now has been redefined, and therefore, the algorithm that we have seen is called the flow augmenting path algorithm. Flow augmenting path algorithm. Now, the flow augmenting path algorithm is simple. So, identify a flow augmenting path, now update the flow corresponding to the flow augmenting path. If there are no flow augmenting paths possible, the algorithm terminates. The definition of the flow augmenting path is any path from the source to the sink which is made up of forward arcs such that the forward arc has excess uij minus xij, and backward arcs if there is an xji in the forward direction and there is a strictly positive flow in this. So, this is how the flow augmenting path algorithm actually works. Then the next thing that we have to do is to show that the flow augmenting path algorithm is indeed optimal. Now, how do we do that? To do that, we first write the primal and the dual of the maximum flow problem, and then show some kind of primal dual relationships that will explain how and why the flow augmenting path algorithm is optimal and works effectively. Now, let us write the primal and the dual. So, primal will be written like this. Let us call f as the maximum flow in this network. So, maxima is f. Now, there are 7 nodes in this. So, as far as this node is concerned, x12 plus x13 is equal to f, because whatever goes out, the total flow that goes out of the source goes out through x12 and x13. So, x12 plus x13 is equal to f, and whenever we have an intermediate node like this, we have flow balance equation. So, for this one we will have minus x12 plus x24 plus x25 is equal to 0. For this we will have minus x13 plus x34 plus x36 equal to 0. For this we will have minus x24 minus x34 plus x45 plus x46 plus x47 equal to 0. For this we will have minus x25 minus x45 plus x57 equal to 0. For node 6 we will have minus x36 minus x46 plus x67 equals to 0, and for node 7 we have minus x57 minus x67 minus x47 equal to minus f, and then we have xij less than or equal to uij, xij greater than or equal to 0. Now, this is the primal formulation for the maximum flow problem. we have deliberately introduced a variable called f, which is the maximum flow. We may actually avoid this f by simply saying maximize x12 plus x13 or maximize x57 plus x67 plus x47. We do not do that. For the sake of some convenience, we introduce a variable called f here. So it becomes maximize f, and then we do this, and then we also need to define whether this f is greater than or equal to 0 or whether it is unrestricted. Now if all xij's are greater than or equal to 0, then it is fairly obvious that f should be greater than or equal to 0. So it makes sense to put f greater than or equal to 0, but we now define this f as an unrestricted variable, which is acceptable because xij's greater than or equal to 0, in spite of the fact that f is unrestricted, xij greater than or equal to 0 will force f to be greater than or equal to 0. Now there is a slight advantage in defining f as an unrestricted variable, which we will see when we actually write the dual of this particular primal. But before that, we also need to look at this constraint. This is an important constraint because whatever quantity that flows in an arc should be less than or equal to the arc capacity. So xij should be less than or equal to uij. Now this is important. There are as many constraints as the number of arcs in the network. Now here there are as many constraints as the number of nodes in the network. For every node you have a constraint here, for every arc you have a constraint here. So if the network has n nodes, m arcs, then there are the xij's, there are m xij's plus 1f, so there are m plus 1 variables and there are m plus n constraints. So this is the formulation of this. We also observe that this portion is unimodular. You can simply add vertically, you will get 0 equal to 0. So this is unimodular, and the max flow problem by itself has the unimodularity property. It is also not so much necessary to define xij as integers because xij's represent the flows on these arcs. So xij's can be defined as continuous variables. So the question of defining xij's to be integers and exploiting the unimodularity property does not exist. We can simply define xij's to be greater than or equal to 0, and the problem will become a linear programming problem by itself. Now let us write the dual of this problem. So the dual of the max flow problem will look like this. Now to write the dual of this problem, we now start defining dual variables. Now there are 7 nodes, there are 7 constraints here. So we can start defining dual variables w1 to w7. So we start defining dual variables w1 to w7 for these 7 nodes, and here we have as many dual variables as the number of arcs. So we are going to define hij as the dual variables associated with this. Now with that in mind, let us write the dual. Now we can always now bring this f into this side of the equation by putting a minus f here, and we can bring this to the other side. So all the right hand sides are 0 here. So this is the only place where we have a right hand side. So the problem will be to minimize, the primal being a maximization problem, the dual will be a minimization problem. So problem will be to minimize double sigma hij into uij. Remember that hij is the variable and uij is the capacity. So the objective function is to minimize hij into uij. Now what are the constraints? Now for every variable here there will be a constraint there. So if we look at a variable, a typical variable xij, or for that matter x12 will appear in the first constraint, second constraint and one constraint here. So the dual variables will be w1 here, w2 here and h12 here. Or in general, if you consider a variable xij, it appears with a plus 1 coefficient in the ith constraint, minus 1 coefficient in the jth constraint, and again there is a constraint which is of the form xij less than or equal to uij. So the corresponding dual constraint will become, for a typical xij, it will become wi minus wj plus Hij. Now this the objective function value is 0, every variable Xij has an objective function value 0. So, it is a minimization problem. So, you will have greater than or equal to 0. So, for any variable Xij you will have Wi minus Wj plus Hij will be the left hand side, the right hand side will be 0. This will be a greater than or equal to, because you have a maximization problem with all Xij is correctly defined. So, you have Wi minus Wj plus Hij greater than or equal to 0. Now, there is also this variable f. Now, this variable f has already moved in here, it is moved in here. So, this will have W7 minus W1, this will have W7 minus W1 is equal to 1, because the objective function coefficient is 1. So, this comes here with a minus sign, this comes here with a plus sign. So, plus W7 minus W1 is equal to plus 1. The equation comes because f is unrestricted here. So, defining f as an unrestricted variable helps us in getting this equation here, and we will see how we use this equation effectively. Now, the dual variables Wj are unrestricted because these are the 7 equations that correspond to the W's, they are all equations. So, the corresponding W's are unrestricted, and then you have Hij greater than or equal to 0, because you have a maximization problem here, you have less than or equal to constraint. So, you will have a minimization problem here with a greater than or equal to variable. So, from the primal dual relationships we can write this as the dual of the max flow problem. Now, what do we gain through this dual, and what is the advantage of putting this equation here, the equal to sign here, by defining f as unrestricted? So, that is the next thing that we will have to look at. But before we do that, let us go back to this network again and try to understand how we define the maximum flow on this network. So, let us come back here to this network. Now, let us try and see what is the maximum flow that is possible in this. Now, if we look at the source 1 first, or first let us look at the sink. Now, all the flow that leaves the source will have to now come to the sink. Now, the sink has 3 edges that get into the sink. The capacities of these 3 are 30, 10 and 20. So, the maximum that can enter the sink is 60 here. The maximum that can enter the sink is 60 here. Similarly, if we go back to this, the source, everything has to leave the source, and you leave the source only in 2 ways. So, through 1 2 and 1 3, the maximum is 80. So, the maximum that can leave this source is 80. So, now this 40 plus 40 80 represents some kind of an upper limit or an upper bound on what can be the maximum flow. So, from this we can say very confidently that the maximum flow on this cannot be more than 80. Now, applying the same thing to the sink, we now can say that the max flow cannot be more than 60. So, now let us look at these two things again in a slightly different context. Now, if we say that considering this source 1, the maximum flow that can happen is 80. Now, it is like saying if I send 80, now or I have the source and these are the 2 edges that go out of the source, now which have capacity of 80. Now, if I remove both these edges, here, if I remove both these, now I have a disconnected network. I have disconnected this network with source on one side and sink plus rest of them on the other side, and I know that the capacity that I have actually pulled out in order to disconnect this is 40 plus 40, 80. So, if I am able to pull out some edges such that I disconnect this network, there is no path possible, then the capacity of those arcs actually give me an upper estimate of what the flow can be. So, I just put it back here to get 40 20 and I get 40 and 35. So, if I remove these two, I know that I disconnect this network, or alternately if I can identify a set of edges such that by disconnecting those edges I am able to divide this network into two parts, then I realize that the capacity of such edges now gives me an upper limit on what my flow can be. The same logic can be used here. Now, by removing these three edges, I can simply disconnect it by all of them here and 7 being there. Now, each of these, now that gives us a capacity of 60, and we can go back and say that the maximum flow now can only be less than or equal to 60. Now, that brings us to another question. Now, when we do this, what have we effectively done? We have, by removing these three edges, we have now created two sets of nodes. One set of node which will be 1 to 6 and the other set of node which is 7, which means effectively the source should always be in S1, the sink should always be in S2. So, this has to be in S1, this has to be in S2, the rest of them can be anywhere. What I mean to say now is, instead of saying I have removed 5 7 4 7 6 7 with a capacity of 60, thereby I have disconnected this network, thereby I have got this S1 and S2 defined accordingly. That is one way of saying it. The other way of saying it is, if I take the nodes 1 to 7 and if I simply divide these nodes into two sets S1 and S2, such that node 1, which is the source, is always in S1 and node 7 or sink is always in S2. The rest of the nodes can be anywhere, and for such an S1 and S2 defined, it is always possible to remove the corresponding edges such that the graph becomes disconnected with S1 and S2 defined accordingly. For example, if I define S1 as 1 2 3 and if I define S2 as 4 5 6 7, which means I am effectively removing this many portion of the graph. Thereby the capacity that I am pulling out is 10 plus 10 20 plus 15 35 plus 20 55. Now, 55 becomes an upper limit for the flow that I can have. Now, it's fairly obvious to understand that we now have a feasible flow with 55, 55 being an upper limit, therefore 55 is optimal. But leave that alone, we can now say that for every definition of S1 and S2, such that the nodes are now divided into two sets, the source is always in S1, the sink is always in S2, the rest of the nodes are distributed. Now, if we are able to get for every possible definition of S1 and S2, it is always possible to go back to this network and find out the removal of which of these arcs will create this and disconnect this network. Now, the capacities of such arcs will give an upper limit on the maximum flow. For example, as I said, if we consider this, then it means that we are effectively removing this, this, this and this. So, we are removing arcs with capacities 55, and therefore, the maximum flow can only be 55. 55 is an upper bound to the maximum flow. Now, what does this tell us? Now, this can be done in multiple ways. It is all about the number of nodes being here, making sure that the source is always in S1, the sink is always in S2, and the rest of the nodes can be put anywhere else. So, effectively we have created two sets of nodes, where the source is in S1, the sink is in S2. Now, we have divided the network or cut the network such that the nodes are now into two sets, and this kind of a thing is called a cut, or it is called a cut set. It is called a cut, or it is called a cut set. So, now for every cut that we can create, or every cut set that we can create, we can go back and find out what is the capacity of the arcs that have to be removed in order to create this cut, and each one of them is an upper bound to the maximum flow. Now, this is the relationship between the maximum flow and the cut, and it is also obvious that we have seen 3 different cuts. Now, the cut here gave us a capacity of 80, the cut here gave us a capacity of 60, while a cut here gave us a capacity of 55. Now, each of the capacities of the cut now gives an upper bound or an upper limit to the max flow. Since each of these gives an upper limit, the smaller the capacity of the cut, the more value and information it gives us, because from this we can say 55 is an upper bound on the maximum flow that is possible on this network. So, the cut set gives us that kind of an information. So, the smaller the cut set is, the closer we are to the optimum of the max flow problem. Now, obviously, since every cut set being a feasible solution gives an upper bound to the maximum flow, there has to be a strong relationship between the cut set and the dual of the max flow problem. Now, let us move now to the dual of the max flow problem and try to map these cut sets with the dual of this problem. So, first let us consider the first cut set, which is made up with S1 equal to 1, the source, and S2 equal to 2, 3, 4, 5, 6, 7. That is, we are going to consider this cut set. Now if we do this here, for every cut set, we can actually find a feasible solution to the dual. How do we do that? For every element which is in S1, for every element which is in S1, we put Wj equal to 0 if it is in S1, and Wj is equal to 1 if it is in S2. So, corresponding to this cut set, S1 will be 0, S2, 3, 4, 5, 6, 7, etc. will be 1, so that this is always satisfied, because W7 is always in S2, the sink is always in S2, the source is in S1, so the difference is always equal to 1. Now, if we go back to this 1, 2, now these are the arcs which we are removing. So, x12 and x13. Now, go back here. Now, wherever Wi is 0 and Wj is 1, so you get a minus 1 here, the corresponding Hij will be equal to 1, that is H12 will be equal to 1 and H13 will be equal to 1, so that this is satisfied. Now, in all other cases, if there is an arc that connects nodes in this, the corresponding Hij will be equal to 0. So, for every cut or cut set, you can get a feasible solution to the dual, and the capacity of such a cut set, if you see, will be Uij Hij. So, that will be 40 into 1 plus 40 into 1, which is 80, which was the capacity of these two. Now, a same kind of an interpretation can be done for the other cut set, where we have S1 equal to 1, 2, 3, 4, 5, 6 and S2 is equal to 7. Now, which means we are looking at this cut set, and now for this cut set we will have W1 to W6 will be equal to 0, W7 will be equal to 1, and we will have H47 equal to H57 equal to H67 equal to 1, and then capacity will be equal to 60. So, the capacity of the cut set will be equal to 60. Now, for the other case that we looked at, the third case that we looked at, we said 1, 2, 3 is S1, 4, 5, 6, 7 is S2. We will have W1 to W3 equal to 0, W4 to W7 equal to 1. Now, these 4 things H24, H25, H34 and H36 equal to 1, so that this is always satisfied, this is also satisfied. So, you get a feasible solution to the dual. The objective function value will be sum of these capacities, which will be 55. Now, it is easy to show that the relationship between the cut set and the max flow. Now, every cut set is a feasible solution to the dual, and therefore, every feasible solution to the dual is an upper bound to that of the primal. By weak duality theorem, every feasible solution to the dual being a minimization problem, is an upper bound to Z star, where the original primal is a maximization problem. So, every cut set solution is a feasible solution to the dual of the max flow problem, and by weak duality theorem gives an upper bound to the flow, and by the optimality criterion theorem or by the main duality theorem, at the optimum the maximum flow and the minimum of these cuts that we have will be equal. So, we get a very strong relationship which is called the max flow min cut theorem, which says at the optimum the maximum flow in the network is equal to the value of the minimum cut, the value of the minimum cut. Now, this is a very important relationship. It is called the max flow min cut theorem, and it is attributed to Ford and Fulkerson, who actually proved this max flow and min cut theorem. So, what we have effectively done is we have taken this example and we have shown here that there is a strong relationship between the definition of the cut and the max flow, and that from here every cut represents an upper bound, and later we wrote the dual of the max flow problem and showed that every cut actually provides a feasible solution to the dual, therefore is an upper bound to Z star by weak duality theorem, and by the strong duality or the main duality theorem we can show that the maximum flow is equal to the minimum cut. So, if the flow augmenting path algorithm is able to get the flows in such a manner that no more flow augmenting path is possible, then we have actually exhausted all the possible flows here, which means we have solved the max flow problem, and we have also got the value of the min cut that is associated with the max flow. Now, coming back to the flow augmenting path algorithm, we defined the flow augmenting path as a path that comprises of arcs from source to sink. If it is a forward arc, then there is a residual capacity, which means there is a difference between the uij and the xij, and if it is a backward arc ij, then there must be a forward arc ji with strictly positive flow. Now, having seen the flow augmenting path algorithm and the way we evaluated all the flow augmenting paths, now the next question is, can we have some kind of a labeling algorithm which will help us program or efficiently get the maximum flow given a network. So, we will now look at a labeling algorithm which we can use to solve the max flow problem. So, let us take a simple network here, so that we can illustrate the labeling algorithm better. So, let us look at a network which So, let us look at a network like this and then try to define or do a labeling algorithm which will help us get the flow augmenting paths. So, the first step what we will do, this is the source, this is the sink. So, what we do first is we first define L1 is equal to minus comma infinity. This is a simple initialization, we do not need to worry so much about it. Now from 1 go to an arc such that there is a forward arc. So from 1 we go to 2. So now start defining label L2 will be from 1 to 2 there is a capacity of 20, there is a flow of 0, it is a forward arc from 1 to 2. So we can increase the capacity by 20. So we put plus 1 and we put 20. Now plus 1 comes because we have looked at arc 1 2. Arc 1 2 has a capacity of 20, right now flow of 0. So plus 1 and an increase of 20 is possible. Now again go back from 2, see if there is a forward arc. So there is a forward arc 2 3. So now look at L3. Now 2 3 has capacity of 10, flow equal to 0. So 2 3 will be plus 2 because it comes from node 2. Now the uij minus xij is 10. Now the earlier value is 20. So take the smaller of them. So you get plus 2 and 10. Now we are in 3. See if there is a forward arc. So 3 to 4. So you will do L4 will be equal to plus 3 because it comes from 3. Now the capacity is 30, flow is 0, so 30 is possible. Now take the minimum of this 30 and this 10, which is 10. Now the moment the sink is labeled, now go back and augment or update the flows. So this the last value that we have here associated with the sink is the quantity of flow that is going to be increased. So we now have flow equal to 10, flow equal to 10. The path will be 4 and plus 3, 3 and plus 2, 2 and plus 1. So the path will be 1 to 2, 2 to 3, 3 to 4 and flow equal to 10. Now update the flows. So 1 to 2, 2 to 3, 3 to 4, flow is equal to 10. Now go back here. Now again start with L1 is equal to minus infinity. Now look at a forward arc. 1 to 2 is a forward arc with 10 capacity, 20 minus 10, 10. So you will do plus 1 and 10. This 10 comes from 20 to 10. Now see if there is a forward arc 2 to 3, there is, but the capacity is 0, so ignore it. Now see if there is a backward arc 2 to 3, right now you do not have here. Then you go back to 2 to 4, there is a forward arc 2 to 4. So you will do L4 is equal to plus 2. Now there is 20 and 0, 20 capacity, but you have 10 here. So minimum of 10 and 20 is 10. Now you see that the sink is labeled, therefore the flow can be increased by 10, flow can be increased by 10, and then you have 2 to 4, 1 to 2, so you have 1 to 2, 2 to 4 with flow equal to 10. Now update it, so 1 to 2 becomes 20, 2 to 4 becomes 10. Now go back and do this again. So you have 1 to 2 you cannot do, so you move from 1 to 3. So 1 to 3 you have 20 and 0, so you put label L3 as plus 2 comma 20. Now look at 3 to 4, 20 is possible, so L4 will become plus 3. The minimum of this 20 and this 20 is 20. Now once again the sink is labeled, so go back and update the flow. So flow is equal to 20. So you have 20 and 20 updated to 20, and this will be also updated to 20. Now this will give us 1. So 3 will be plus 1 20. So this will give 1 to 3, 3 to 4, and flow is equal to 20. Now see whether you have any other possibility. So 1 to 2 you cannot move, 1 to 3 you cannot go. So, you no more flow augmenting path exists, and therefore, you get flow equal to 20. So, the one thing that we have not actually shown in this example is how do you get a backward arc into the picture. Now, if you want to do that, then if for example, if at some point we have say suppose we have a 20-20 here and say you have 25-20 here. Now, if we did the labeling algorithm, even you have 10, 1, 2, 3, 4 you had 10, and 1, 3, 4. Okay, let's redo this. So, we had 1, 2, 3, 4, 1, 2, 3, 4 with flow 10, which is correct. So, we had 1, 2, 3, 4 with flow 10, 1, 2, 3, 4 with flow 10. So, let us have the capacity here as 20. Then we had 1, 2, 4 with flow 10. So, you have 20 here, 1, 2, 4 with flow 10, and then we have 1, 3, 4, 1, 3, 4 with flow 10. So, that this becomes 20 and this becomes 10. So, if we have this network with capacities 20, 10, 20, 20 and 25, and 3 iterations of the flow augmenting path would have given us something like this. Now, go back and look at a flow augmenting path like this. Now, L1 is labeled as minus comma infinity. Now, we realize 1 to 3 is a forward arc. So, I can label L3 as plus 1 15 that I have here. I can do plus 1 and 15. Now, 3 to 4 I can't have a forward arc because this is full, but I can do 3 to 2 as a backward arc because 2 to 3 is a forward arc with flow equal to 10. So, I can go back and do L2 as plus 3 and minus 3 and 10 here. Now, this minus indicates that it is a backward arc and 3 indicates that it is coming from 3 to 2 backward arc, which means 2 to 3 forward arc. So, now I have reached 2. Now, I go back here, I can label L4 as plus 2 with a gap of 10. 10 is smaller, the minimum of this 10 and this 10, which happens to be 10 here. Now, I can increase the flow further by considering 4, 2, 2 and then 3 and then 1. So, 1, 3, 2, 4. Now, 3 to 2 is a backward arc. Now, flow will be equal to 10 and we can update this as this becomes 20, this becomes 0 and this becomes 20. So, we can define this labeling algorithm to handle both flow augmenting paths that are made up entirely of forward arcs as well as flow augmenting paths which have a combination of forward arcs and backward arcs. We saw the other example right now how you model a backward arc. So, you do 1 to 3, 3 to 2, 2 to 4 and then increase the flow here by 10, reduce the flow or divert the flow and bring it back to 0 and then increase it to 20. So, this is how the labeling algorithm for the flow augmenting path works. Now, so far the labeling algorithm as well as the flow augmenting path algorithm are very good ways to solve the maximum flow problem, but are there limitations to that? Now, we can see that through a very simple example. If we consider a very simple example where let us say this has a capacity of 1000, this has a capacity of 1000, this has a capacity of 1000, this has a capacity of 1000 and this has a capacity of 1. and if we apply the flow augmenting path algorithm, we realize that we could start with 1, 2, 3, 4 with flow equal to 1. So, you could get a 1 here, a 1 here and a 1 here. Then we may consider 1, 3, 2, 4 with a backward arc. So, this becomes 1, this becomes 0, this becomes 1, flow equal to 1. Now, again we can consider 1, 2, 3, 4, again we can consider 1, 3, 2, 4 and so on, and then we realize that we actually require 2000 iterations, with each iteration augmenting the flow by 1 unit to get a maximum flow of 2000, which is possible here. So, in some sense the flow augmenting path algorithm is not a very efficient algorithm when it comes to running time as indicated or shown by this particular counter example. So, the flow augmenting path algorithm, the way we defined, would actually the extent of computation would actually be dependent on the maximum of these capacities. So, later people came up with refinements where we looked at what is called shortest augmenting path algorithm, where we always find an augmenting path which has as few edges as possible. We realize that sometimes a wrong choice would lead to solutions which require backward arc flows. If the paths are chosen very carefully such that then there can be no need, or there is no need for a backward arc path. So, the shortest augmenting path algorithm will try to first exhaust all the forward paths with increasing number of arcs inside, and only when absolutely required will evaluate arcs that require backward arcs, or will evaluate paths that would require backward arcs. If we apply the shortest augmenting path algorithm, we straight away do 1, 2, 4 with flow equal to 1000, and we do 1, 3, 4 with flow equal to 1000. So, this would ensure that we first exhaust all the forward arc paths and we go to backward arc only when it is absolutely necessary. In fact, this would not even evaluate a backward arc path. So, the shortest path augmenting path algorithm is actually an improvement over the normal flow augmenting path algorithm, but the flow augmenting path algorithm helps us understand the maximum flow problem and its implications from an OR point of view very well. So, in the next lecture we will see the minimum cost flow problem and continue our discussion in OR models.